Hello students, welcome to Module 7, in which we will discuss electrochemical laboratory techniques. The learning goals of this module are the following. You should be able to select the most suitable laboratory technique for a certain electrochemical investigation. You should be able to interpret a voltammogram. You should be able to determine diffusion coefficients from rotating ring disk electrode data. You should be able to determine tafel slopes from a Kautokeylevich plot, and you should be able to determine the selectivity of a reaction from rotating ring disk electrode data. Now, let's start with the first part of this module, in which I will describe the different electrochemical laboratory setups that you can use for your experiments. The first setup I will describe is the parallel plate setup. This is the setup that most closely resembles industrial electrolyzers. And basically it's schematically represented here. You have an electrode plate, then you have the electrolyte, you have a membrane, you have another electrolyte channel, and then you have the cathode. And here is how such an electrochemical setup looks like. It's a bit difficult to see, but basically you have a plate, an electrode plate, then you see these green gaskets that are basically where the electrolyte is flowing through, but of course you don't want the electrolyte to flow out of your setup, so you need some rim, the gasket. Then you have the membrane also sitting here, and so you build towards the cathode on the other side. And typically these cells are quite long, so this picture is actually a bit confusing because now it seems that the cell is quite thick and quite short, but in practice you see this is only 3 mm and these cells can be quite long, so in practice they look like this, so this picture is a bit confusing. This setup using a parallel plate setup, that's really an important step if you have developed an electrochemical process in the lab and you want to scale it up, then this is really what you need to do first at a smaller scale, and you can gradually increase the size of your parallel plate. The advantage of this setup is that you have a reasonably well described mass transfer. It can still be a bit complex, as we discussed in the current distribution module, but it's reasonably well described, and you can use the mass transfer correlations we have discussed before in module 5.2. Although the parallel plate setup is a nice setup, it has its limitations. If you, for example, want to investigate a new electrode material for a certain reaction, you might not want to start with the parallel plate setup. And why is that? Here I give a couple of reasons. This is a parallel plate setup. You see it's relatively complex. Here's the cell, but you need a pump and you need possible flow meters. If you produce a gas, you need a gas outlet with a gas meter. You need storage tanks, you need a possible gas liquid separator. So it's quite a lot of equipment, and so it's quite complex to realize such a setup. Then another important disadvantage is that you measure the complete cell potential. If you're only interested in an anode or a cathode material, then you rather see only the potential of that particular electrode with regard to a reference and not the complete cell potential. Then, although we have a reasonable description of the mass transfer, it's not perfect, and we still suffer from inlet effects. And if you form gases, then the description is relatively poor. So that is another limitation. And there can be certain concentrating gradients in the setup. So there are quite some limitations. If you want to use a parallel plate setup for testing electrode materials. So what else to use? Actually, when investigating, for example, an electrode material, you want to go to a much simpler setup, but a setup that allows you to really set the potential of your electrode with regard to a reference electrode, because then you can really investigate this one particular reaction. And for that, you can use what we call a 3 electrode cell. And that one is depicted here schematically. You have a working electrode, a counter electrode, and you have this reference electrode. And here you see a photo of such a setup. And what this setup now allows you to do is that you can set the potential of the working electrode with regard to the reference electrode. Now you might wonder, why does it say working electrode and not cathode or anode? That is because it depends on the potential you apply to the working electrode, whether it behaves as a cathode or an anode. And it's very well possible that in your experiment you change it from being an anode to a cathode and vice versa. So that's why we call it the working electrode, the electrode we want to investigate. The counter electrode is only there to make the cell complete. If you have an oxidation reaction on the working electrode, you need the reduction reaction somewhere, and for that you use the counter electrode. So this is the most common type of setup in an electrochemical laboratory. You see them very often in all kinds of different shape, but they always have the same principle, where you have a working electrode, a counter electrode, and a reference electrode. And that's because you want to apply a certain potential or a certain current to the working electrode. Now, here I recommend you to carry out quiz question 7.1 to get to get a bit more familiar with the purpose of the Lugin capillary, which is an important part of such a 3-electrode cell. A 3-electrode experiment is not possible without a potentiostat. This is the machine that controls basically what happens between the reference electrode, the working electrode, and the counter electrode. So it controls what's happening in this green box. And here you see such a device. And basically with the potentiostat, it's possible to apply a certain potential to the working electrode with regard to the reference electrode. And that's what you want to do. So we need a potentiostat for that. In this course, we will not go into the details of a potentiostat. That's electrotechnical work, which is outside the scope of this course. As I just mentioned, there are many types of 3-electrode cells you can find in an electrochemical laboratory. And what is interesting to mention, that it's also possible to combine these 3-electrode cells with spectroscopic techniques. For example, by combining it with a mass spectrometer, or by combining it with infrared measurements. And people have really done very nice work to really combine them, to really make these in situ experiments. And you see that then these setups can become more complex, but they still always have the principle of the 3-electrode cell. Also here with this OLEM setup, which stands for online electrochemical mass spectroscopy, you still see the counter electrode, the working electrode, and the connection to the reference electrode. So this always comes back. But with this combination with spectroscopy, you can combine electrochemical and spectroscopy experiments, and especially for work on electrocatalysis, this can be very valuable to obtain more mechanistic insight. A potential disadvantage of the 3-electrode cell is that it has rather poorly defined mass transfer. If you just hang an electrode into a beaker, the mass transfer of the reactants to that electrode is not properly defined. So if you want to have really good definition of the mass transfer to an electrode in a 3-electrode cell, you have to use the rotating disc electrode. And why does it have very good, well-defined mass transfer? Well, you rotate the electrode and you get a flow pattern like this, and this flow pattern is very well defined. And then because of that, it's really easy to describe the mass transferred to the electrode. Now, we will do this extensively in the third screencast of this module, where we will discuss the rotating disc electrode. So we will come back to this. Now for a completely different setup, which is the H cell. And well, you can see why it has this name. It has this H shape. And we use the H cell to study membranes, the red thing here in between. And it actually consists of 4 electrodes. We have the anode, the cathode, and now we have 2 reference electrodes. This one, that one. And both of these reference electrodes are positioned, their tips, the loop-in tips, are positioned very close to the membrane. And this allows this setup to study really the potential drop over the membrane without being disturbed by the ohmic drop over the solution. And this you can, for example, use to measure the potential drop over the membrane as a function of current density, or you can see what the influence is of concentrations on the membrane performance. So that's why in this case you use a 4 electrode setup for these for this H cell. Now you probably wonder, what setup should I use when? Of course, I already gave you a lot of hints during the previous slides, but to make your life easier, I've made this overview. So if you're interested in studying, for example, a new anode or cathode material for a particular reaction, and you have a system where mass transfer is not expected to play a large role, for example, because you operate it at very low current densities, where you always have sufficient mass transport from the bulk, then I always recommend you to use this simple 3 electrode cell, which allows you to really accurately set the potential of the working electrode with regard to the reference electrode. And that's what you need for those type of measurements where you want to study over potentials. Now, if however you operate at higher current densities in a system where mass transfer can be limiting, then it's time to go to the rotating disk electrode, which allows you to study diffusion coefficients, electrokinetics, and selectivity. Well, here it says RRDE, that stands for rotating ring disk electrode. And as said previously, I will discuss the rotating disk electrode much more extensively in the third screencast of this module. So wait for that. Then, if you're interested in membrane performance, you go for the H cell. And as the last option, if you're interested in the complete cell, then you go for the parallel plate cell. Now, I also want to mention here that it's not always a parallel plate cell. For example, if you're interested in a gas diffusion electrode or these porous electrodes, then it's not a parallel plate cell. But still, the type of cell is the same. Then you could call it a 3D electrode cell, but it still applies the same logic. You have an anode material, you have the membrane, you have the cathode material, possibly separated by electrolyte or electrolyte in the pores, and there you really minimize the ohmic resistance between the parts. So this is where I would like to conclude the discussion on the different setups that you can use, and the next screencast will be on the techniques you can use to then gather information. So thank you for your attention.